I will talk today about something some of you have seen me talk before, so I apologize to those of you that didn't know Jochen when I was in Oxford. I gave a very similar talk. I wanted to talk about something else, but didn't get to it in time. So here's something I want to talk about. I hope what I want to do here is kind of, before I really kind of start about the technical details, I want to kind of motivate it. I mean, this is what's definability, decidability, and computability, and I want to kind of introduce my kind of the motivation from all these three viewpoints. So even if you kind of don't care too much about the details of my talk, and maybe at least get the motivation. So one way of looking at this is kind of a very modern theoretic point of view, is that when I started my PhD in Oxford now 20 years ago, with Alex Büchi, he was looking at a complex field with exponentiation. I mean, this is Silber's conjecture that definable sets are either countable or co-countable if you expand the complex field by exponentiation. Back then he had this kind of very simple case, I'm not sure you've ever written it up, which was if you take not full exponentiation, but just raising to power I, so as a predicate, of course. So then he knew that this was quasi-minimal, so satisfied this property of countability and co-countability. So he pointed out that, or he used for that the real field together with the analytic functions and a to the z. So a here is the real number, and you raise it to any integer power. So you take the set of all integer powers as a further predicate. He used the model completeness of this structure in his proof of the quasi-minimality. So naturally he wanted to extend this to more power functions. So not just raising to power I, but some kind of other complex number. So his question was, okay, if I want to do this, what I really need is to expand this structure, that's the structure over the reals, by raising to more powers. And he asked, okay, if we add such a power, can we then preserve model completeness? The answer was unfortunately a resounding no. So I proved by myself, especially in my own PhD, that if you take the real field with two integer power, with two predicates, where each of them is raising to powers of different real numbers that are suitable independent, so that they're kind of not rational powers of each other, then you define the integers. And of course, if you think about this, if you have such a structure and you add a power function, then you get, and simply the image under the power function f a to the z gives you another of these predicates, and the method was hopeless. Very luckily, very recently, Bernard and Kirby, they kind of solved this problem by a completely different method. So they kind of followed more the Boris's way of handling the structures and analysis. Okay, but so this was kind of the background. The question I'm really interested in now is kind of, okay, I understand that this doesn't work for this, but I'm interested in studying these kind of structures because they kind of appear naturally. So this kind of, we have our universe and you add discrete groups. Okay, this should be really not Z here, it should be N. And so they can ask us about many other structures, and that I want to do today. There's, of course, if you want to look at this from a decidability point of view, that you can do too. I mean, if take the theory of natural test natural proof, that's very well known to be decidable, that's Presburger's result, but Gödel or Church, the theory of the field is of course undecidable. So you can ask this a very natural question, and this is kind of an old program in logic. How much of multiplication can you add to Presburger without getting undecidable? It's a different, if you think about Hilbert's 10th problem, or kind of the whole program there, you're trying to drop the number of quantifiers you're allowed to use. Here the program is to make this predicate here smaller. The first result, and this is really kind of an easy exercise if you think about this and you know the binomial formula, is the following. It's Putnam's result is that if you add to the Presburger the set of squares, then the resulting theory is already decided. So if you really take a not even that you take squaring as a function, but yet even just a predicate is enough. Squaring is easy to see, that's really just one more formula, but square, to get the set, you have to at least, it's kind of an exercise you can give in a logic course quite nicely. So closely related to that, but we'll not talk about that today, is also you can do the same things over the reals, where you kind of, the structure where you have the reals with order plus and the natural numbers, that is model theoretically, or definability, or decidability and well behaved, but of course there if you also add full multiplication, you're very much in trouble. Alright, so I have now the definability viewpoint, the decidability viewpoint. There is also a computability viewpoint, or let's say something, theoretical computer science viewpoint that I want to connect it to. And this connects to Cobham's theorem. Cobham's theorem is really one of the classical results in theoretical computer science. And I will state it, and I will take the next time about 10 minutes to explain how this really connects to it. So Cobham's theorem stated if you have two natural numbers, or integers, then k and l, and you know that they're multiplicatively independent, then it said x is both k-recognizable and l-recognizable if and only if it is ultimately periodic. Okay, I have to say a couple of things. First of all, I hope that for logician this is kind of obvious. The set is definable in Presburger arithmetic if and only if it is ultimately periodic. So the kind of you can directly replace and say this again in a second. Ultimately periodic with definable in Presburger. So what is a k-recognizable set? I don't want to go into all the details, but I'll give you a couple of examples in case you've never heard of these things. A set is k-recognizable if the language consisting of the base k representation of elements of x, so you take all of them, possibly leading 0, is accepted by a finite automaton. The two examples I have is the first of all is k to the n. Okay, what is a, you really have never seen a finite automaton. Finite automaton is a finite state machine, and in this case you give it a sequence of 0 and 1s, and depending on, and it reads it one after another. So if it reads a 1, for example, you start in this state, if it reads a 1, it stays in this state, if it says a 1, then it moves over. If, for example, as in this state, if it in this state and reads another 1, then the computation stops and we say it failed. So I kind of don't add a fail state. So I always assume that if the errors are not drawn, then the computation breaks. And if something is accepted, if you end with your computation in this kind of double state, this accept state. So you can read, so the powers of k are obviously, if k is, let's say, is 2, then it's just the sequences of 1s, the sequence of 0 and 1s, where there's 1. This is accepted. You can even get more complicated states, so maybe the powers of k we have seen before. You can also take some things like what is called the two-more set. That's basically take all the natural numbers whose binary digit sum is even. So binary digit sum really just means that you count the number of digits in the binary representation. And I don't want to go too much into it, but you can see that this automata recognizes a set, because you start in here, you have no 1 in the representation yet, and you have a problem if it's odd, so you're not in a final state, so this makes sure that you always move around, have to move back in order to accept.
Can you have more than one accepting node?
Yes, as many as you like. Okay, good. You can do the same game for higher dimensions. There you have to be a little bit careful about how you set it up. A base k representation of a tuple is not a tuple of words, it's a word over the alphabet, where the alphabet consists of tuples. So it's a word of tuples and not a tuple of words. So for example, the base 2 representation, if you take 6/3, then this here is the representation of this vector. Doesn't matter too much, but this is how you set it up. And then, of course, you say in a similar way is that x n to the n is k-recognizable if the corresponding language of the base k representations of x is really recognizable. Okay, Semilinear in 77, he generalized Cobham's result to higher dimensions, and so that k and l be again multiplicatively independent. Then x is both k and l recognized if and only if it's semilinear. Semilinear is actually quite kind of is something of the following form. But for us logicians, I think the only case we care about is that it is again defined. Yes, please.
For k-recognizable in higher dimensions, then like before we just substitute between if the digit is 0 and if the digit is 1, we have to have an exhaustive list of every possible thing, like if the first digit is 1 and the second digit is 0, do this versus. Okay, so we just list all those?
Yes. Okay. So the kind of the automata over the errors, they would see kind of tuples.
Okay.
Right. So really what this kind of is that if you show this k-ary, if it is Presburger-definable. So we can kind of these conditions here on the second part, we can always put in kind of first order terms. K and L recognized we can also be put in first order terms, and I'll do now. That is usually done through Büchi arithmetic. This is kind of the easiest formulation to write it down. It's not necessarily the easiest to understand. Maybe for valuation theorists, this just means that you add a valuation function. So for k and then that vk with a function that maps any natural number to the largest power of k dividing x. Okay. And then this goes really back to Büchi. Okay. And it is shown there that if you have a k-recognizable, this happens if and only if x is definable in vk. I don't want to give you a proof of this, but I just give you two examples. We had, for example, k to the n, and of course that's really easy to get. That's just all the natural numbers whose valuation, in this sense, is the number itself. A little bit harder to see. And I give you the formula. Let x be the set of all x and y such that x is in 2 to the n, so it's a power of 2, and x appears in the binary expansion of y. So if you want to see this kind of, the idea is that you have y, and then x has to be a power of 2. Okay, that's easy. And then you split up y into part x, x in the middle, z and t. You have to make sure that the valuation of t is larger than x and x is smaller. So you really kind of split it up in parts where you know they don't contribute to in this case x digit. Okay, but you can do this. And so then Büchi showed, it's a corollary of its actual theorem, is that this theory is decidable. It follows in particular, and this is what we're going to use, that the theory of the natural numbers plus x, if x is recognizable, is decidable. This is really kind of this. You can do this because you have this translation now between, and this is an effective translation between definable sets and automata. And for automata, you can check emptiness. And this is also kind of it's really kind of a transform the first order formulas to automatas and then decide a statement about automatas. Okay. Nowadays, they're often called automatic structures. That's really what this means. Something that you can represent in an automata. They always have decidable theories. So if you now, in particular, if you take Büchi result from the first, what that means, you can now restate Cobham's semilinear completely in first order form. So if you have k and l independent, and you have x is both definable in Büchi arithmetic over k and Büchi arithmetic over L, then it is Presburger-definable. That is Cobham's semilinear. So what is the connection to powers of 2 and powers of 3? First of all, they are 2 and 3 recognizable, but they will allow us to show this result. So this is kind of now what I want to talk about, and it's kind of the strong form of Cobham's result. So you know that a set cannot be k and l recognizable at the same time. Okay, but what you don't know yet, or that doesn't follow from that, if you take both k-recognizable and l-recognizable set, and you put them over Presburger, are they undecidable or not? A priori, wasn't clear, but this is indeed true. So if you take k and l independent, you have a set x that is k-recognizable and l-recognizable and not Presburger-definable, then the corresponding theory is undecidable. That's just a restatement of this in terms of first order form. So if it's not defined when k Büchi arithmetic and the other one is an L Büchi arithmetic, but not Presburger, then over Presburger they're undecidable. Cobham's theorem follows immediately from that. In some sense, I mean, the proof of Cobham's theorem, at least from the original ones, are really hard. They're now easier proofs because they're purely combinatorical. But here's this is the nicest or shortest logical proof, assuming this kind of heavy result, which says that if you have x is definable, fx is definable in both, so it's k and l recognizable, but not Presburger, then the corresponding theory has to be undecidable by this result. We already said that it follows from Büchi's result that the theory must be decided. All right. So let me try to give you now a proof of this result, but first I want to really reduce again to this the same motivational question I had before about the powers of 2 and powers of 3. So Villemaire in '92, he showed that if you take and then Presburger with Vk and Vl, that basically means that you take Presburger and you add all k recognizable sets and all l recognizable sets, then the corresponding theory is undecidable. Bès improved that to the case that if you have k and l multiplicatively independent and y be defined as k as l recognizable but not in Presburger, then the theory of the structure where you take all k recognizable sets and a single l recognizable set that is not Presburger, you're undecidable. In both cases, that's a point this out. This is the structures define multiplication. So hence, undecidability follows from Gödel's theorem, or if you like, Hilbert's 10th problem. But it always goes to multiplication. And here's the picture again. I mean, here in the middle we have Presburger, and yes, sir, please.
So if I understand what you're saying, it's enough to define multiplication by arbitrary naturals. It's enough to define multiplication by any, or exponentiation by any two naturals.
No, that's actually not. So this is this what I'm saying here is currently that if you have this V caliber, so a k.
Oh right, it doesn't just define exponentiation. It also gives you at least power k that's less than.
Yes. So this here is quite powerful, and this could be just what is it, L to the n.
Okay.
That is right. And so this the picture. You really the status was that you had Vk and one y, and now I really want to do it to show this. Wanted to do it to one x. I will not. So I will show. Where is this here? This is. Okay, I wanted to do this first. Sorry. So this is this theorem again. That I want to prove, so now I really want to do it for this x and y. But there's one big thing that makes it much easier, at least for me, is that Bès in his paper, when he showed that the y was enough, he showed that if you have a set X definable in Büchi arithmetic over K that is not Presburger, then you also have K to the N definable here. So really, what you really have to show to prove this kind of strong version of Cobham's theorem is kind of the same thing that was asked before. So really what this boils down is that you have K and L independent, and then the theory of N plus Kn and Ln is undecidable. Then you get the kind of this whole strong Cobham. And as I said, this is really in kind of in logic and model theory. Maybe it was an old question from at least the early 80s. Okay. In some sense, before I go, this might, with the number theory comes a little bit more explicit, but we come back to that in a second. This is kind of unfortunate. I mean, it's even the theory of where you take K and L to be 2 and 3 really includes non-trivial number theoretic statements. So, for example, here's a corollary of Baker's theorem on linear forms. I will come back to Baker's theorem a couple of times. Is that for every m in N, there exists a constant Cm, such that if n1 and n2 are the powers that are raised 2 and 3 to, supposing that if the difference is m, then n1 and n2 have to be smaller than this constant. So what this says is that if you take powers of 3 and powers of 2 and look how the difference between them goes to infinity, then this grows up to this cannot. There's no large powers of 2 and 3 that are close to k. Baker's theorem is fields model building. I'm not aware of a proof of this. This is a corollary that doesn't use Baker's theorem. But that seems kind of, you would assume that you can remember.
There is an earlier proof of this.
Okay.
But it's ineffective, and it doesn't give you
the constant.
This follows also from Siegel's theorem about integer points on curves, which is earlier than Baker. But it doesn't tell you how to compute C.
Okay. Then it's kind of Siegel's theorem. And this kind of you can express explicitly. Now I turn it around to confuse you. So for all, what it says is that for all u, where u is kind of the distance, there exists a v, such that you cannot, if you find x and y larger than this v, larger than cm, then the distance has to be at least u. Then this kind of, if it's Siegel's theorem, then it's maybe not right. I don't think Siegel got a fields medal for this, but what this kind of maybe means is that you can automatically prove theorems worth a fields medal, because you can, if you put this in kind of the first of the theory, and this would be decidable, then you would be able to automatically do this. It's kind of, I mean, there are kind of interesting structures where we still do not know whether they are unconditionally undecidable. For example, if you take powers of 2 and powers of 3 and replace this by the single predicate of primes, then the twin prime conjecture is expressible in this, but we do not know whether the structure is undecidable. We know that the theory of that structure is undecidable under Dixon's conjecture, which is basically saying that all these things are true. Okay, so I want to go this case, but I want to so now I copy-pasted the slides at the wrong place, and I corrected this morning, but then my overleaf account timed out. So here is the it's on the wrong place. So I will not define multiplication. So I want to now prove undecidability in the structure of powers of 2 and 3. I will not show that multiplication is definable. Actually, when my students show that you cannot define multiplication, when I come back to that later, what I will do is I will basically interpret, if you like, the halting problem, but for me it's always kind of this monadic this theory that I know that is undecidable. So this is what I call the monadic second order of the grid. So this is it's a two-sorted structure, so it is two universes, the power is the n squared and the power set of n squared. It has two successor operations, one where you kind of go to the right, that is the first one, and one when you go up. And this is really an exercise. This is an undecidable theory if I can give you a proof sketch, I mean, basically what you always do is you encode the halting problem. So you take your favorite way of taking Turing machine, and then you take subsets of n squared and use them to encode things about the Turing machine. So the AIs store the state of M. So ST is an AI if and only if M is in state I, and its head is over the T cell at step S. Okay, so it is so this guy saves the state, and so you also have to save what is in the register. Or on the tape, and this if you do it with Turing machines, if the BJs code the symbols on the tape, so ST is in BJ if and only if J is on the T cell at the S step. And now you basically, if you want to say, okay, I have a run on a Turing machine, all you have to say is, okay, there exist these sets A1 to AM, B1 to BM, and then for all steps that you can do easily, because you have kind of the natural numbers around here, you say that the transition works out under this assumption the machine is in that state. So the halting problem is really easily to code in this structure. Okay, so what I will now do is I will show you how to code this kind of grid with powers of 2 and powers of 3. Now I have to go to the right spot. Okay. All right, so we do it for powers of 2 and powers of 3 because that's kind of the easiest way, but it works really in a one. We have to take two functions. I think the first one is very easy to understand. It's kind of the floor function. The floor function powers of 2. So you take x and map it to the unique power of 2 that is such that x is between power of 2 and the successor. That is really more complicated. Is the second thing we need? And it's more kind of it defines the set for every y to the n. So it's up there. This is the formal definition, so that you can define it in the structure. But really look at this. So the set of y, set as y, is a set of all powers of 2, such that y is the second largest power of 2 that appears in the binary representation. So really what I care about is I take a power of 3, write it in the binary expansion, and I care about how large is the jump between the first and the second digit. So for example here, this is as far as I can compute it easily, if you take 27, then you write that 16 plus 8 plus 2 plus 1, and so that means that 27 is an S8, because 8 appears as the second largest digit in the binary representation of 27. These sets are always finite. It's follows from, again, Baker's theorem, maybe Siegel's theorem. However, the size growth, that was to me absolutely not clear before we tried to prove this, is that for each y this is infinite, but for all m and n finite, because kind of the difference between powers of 3 and powers of 2 becomes larger as you go to infinity. However, for all m and n, there is a y such that if you're larger than m, you can still find something that has more than n elements in Sy. Yes, please.
So, what do you do if there's not a consecutive jump? Like, what's S of 9 look like? That would just be 8 and 1, but there's no jump in the power of 2 there?
Sorry, say again, S of?
We're looking at powers of 3.
Yes.
So where's 9 live? Because that binary, or that base 3 expansion, or that base 2 expansion is 8 plus 0 plus 1. But there's no, consecutive jump there?
S is defined only on powers of 2.
Yes.
Oh!
So it's really, I care that I have to have the representation. I mean, you could do this for
okay.
And the point is, why this is kind of interesting, is that this is very generic. So this kind of, you have this for each power of 2, and you have this finite set, so you have this kind of you have these powers of 2, and you have all these different finite sets, and they interact in kind of a random way that allows you to encode many things. I have a picture which I think is more clearer than with the statement of the lemma. So here you say, really what you want, you have to take 1 to n, you take a partition, and then you can find a power of, basically power of 2, that's what the S encodes, and powers of 3, such that in between 3 to the t1 and 3 to the tn, so among this n powers of 3, that for each, they don't have to be consecutive, there could be many jumps, but that for 2 to the s plus 1, you get exactly 3 to the tj in this set, if and only if j is in zy. So for example, if you give you here the picture, so n is equal to 10, m is equal to 4, you take this partition of 1 to the m, then you can find an s, and then take the consecutive powers of 2. This is really kind of important that you have consecutive here, you don't need it there. And you can find, so you find s and t1 to tn, such that you can basically pick it in any, you fulfill this pattern here, this partition. So basically, you can give me a picture like this, and I can give you the powers of 2 and powers of 3. In this case, and that's kind of not directly obvious, this allows you to encode arbitrary large tuples of finite subsets, but the idea here is really just kind of, where do I have it? So that, right, so this kind of, maybe this, let's say it like this. This is the x value, this is the y value. So this here encodes 1, 1, because it's kind of the first thing in between the x's in the top row. This encodes the 1, 2 value, because it's still in the first kind of between the two x's, but in the second row. And then here's some, this is 2, 1, and this is 2, 3, and so on. So it allows you to code arbitrary large subsets of 2, and that is enough to code enough about the grid to get the undecidable. So this is kind of really, you have powers of 2 and powers of 3 are generic enough to encode this. This kind of method is really kind of, it doesn't define multiplication or anything, it just tells you that somewhere there is this kind of complexity. All right, how much? Okay, good. So that is kind of all I wanted to say about the proof. But I said at the beginning that the previous proof went over defining multiplication. And in this case, really, my student Chris Schulz, they showed that multiplication is actually not definable in there. And they did this by showing that in the structures, definable sets have a certain property. And for this, I have to introduce over the natural numbers a notion of smallness and of largeness. The notion of smallness, if you're a number theorist, I hope you will see this. The set x has 0 natural density if the lim sup of this is equal to 0. I mean, there's upper and lower natural density. I really don't care about all this distinction, and they could have density 1/2 or something like this. I really just need this definition for equal to 0. And so this kind of are small sets. Piecewise, the set is piecewise syntactic. It's now the notion of largeness. If there is a B such that there are arbitrary long intervals of Z where the gap in X is bounded by B. Arbitrary long intervals of Z, but the gap is bounded. This is syntactic is a stronger property, so this is kind of where the arbitrary long intervals come in. That is kind of the piecewise. So that's our notion of largeness. And now you can think about, until I reveal the answer at the end of the page, can you find an arithmetic set, so a set definable in the naturals with plus and times, that is neither nor. Okay, and so Chris, they showed what I call Friedman-Miller for Presburger. So it's a version of a result that Friedman and Miller proved for the reals, and they showed it for the integers. So what does it say? It basically says that if you have a set E, and you know that under Presburger-definable maps, the image is small. Whatever you do with it, with any power, and you map it under Presburger-definable map, you stay small. In particular, E itself has to have a natural density 0. Then they showed that I'll say what the hashtag is in a second, that every subset definable in here, in the line, as in Z, is either large in the sense above or small in the sense above. So either piece van de Dekkers or zero natural density. The hashtag means that you not only take either to the structure, but you add every subset of every power of E to the structure. So you not only take E, you take any subset of E to the n and put it to the n, then the statement is still small. So that means that if you start with a small set, then everything is either large or small. So what Chris then also showed was if you take E to be the union of powers of 3, then you can show that the image of E, or E to the n, under any Presburger-definable has natural density 0. So in our setting, you can say it's not so hard to see that you can place k to the n, l to the n by the union, or you could even get it back by using the hashtag. You know that they satisfy this property. Okay. So now you need the arithmetic set. What is there? Anyone want to say what the arithmetic set that is neither piecewise synthetic or... Okay, one of them that definitely works. If you take the sets of square-free integers, this is neither piecewise synthetic nor does not have zero natural density. But if you would define multiplication up in the structure, then you would define the square-free numbers, the arithmetic set, but they still not satisfy the conclusion of Schulz's theorem, so you cannot define multiplication. It's kind of a really nice. You could, I always wanted to, as you know, I'm kind of more coming from the minimal side. I always wanted Chris to develop, but he never did. He wanted to develop some kind of tame geometry here, because the piecewise synthetic is large. That corresponds over the kind of an ordered structure of the reals to having interior, and zero natural density corresponds to small. So that would be something like, I don't know, nowhere dense or something. So it's either interior or nowhere dense in the reals. And so I would guess that you can develop at least rudimentary tame geometry over Presburger in that sense. Yes, please.
So I'm trying to wrap my head around piecewise synthetic. So, for example, we don't have to have our intervals centered at 0, right? Like the characteristic function 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1. That wouldn't be piecewise synthetic because the consecutive ones are those intervals where the gaps are bounded by 0.
I think that is correct. Yeah.
Okay.
Okay. I do want to talk briefly, I should have made this explicit at some point. The naturals define, of course, order, because you simply can say one is smaller than the other. If you can find another integer, so x is smaller than z, if you can find a y such that x plus y is z. But in the integers, that trick, of course, does not work. So the integers do not define order. Gabe Conan, really kind of purely, I think, more theoretically motivated, studied the theory of the integers, so as a group, so without order, and powers of k and powers of L, and he showed that this is super stable with U rank omega. Okay, I do not want to tell anyone what this precisely is. That means it's kind of in the Shalab theoretic sense, it's combinatorically stable. That's what it means. But it's kind of, he uses kind of really advanced tricks, at least for me, from stability theory. So I always was wondered, okay, what about decidability in this setting? And so a student of mine, a master student in Fang in Sil-Urbana, and now Michael Reitmeier here in Bonn, they showed that the theory of this structure is decidable if and only if you can solve the following computational problem given a linear equation, okay, where you want to find solutions in the union of these powers. It's like a very easy question. And you want to, you're able to compute the set of non-degenerate solutions. Non-degenerate just means that no subsum sums up to 0, because otherwise you can just scale it and still get another solution, and you get infinitely many. It's long known, okay, but also that is kind of a really big theorem in number theory, is that you always have finitely many solutions. For each a1 to an, you have finitely many solutions, but that of course doesn't mean that you can compute them. And so this was recently solved, in some sense, by a group of theoretic computer scientists, and they showed that such solutions are indeed always computable, and they used that to show that the existential theory of the structure we are looking at is actually decidable. So the undecidability result that Chris and I have from for powers of 2 and powers of 3 for the whole theory, really that needs, as they pointed out, the EAE fragment. The existential statement, the existential theory, that is decidable. So Hilbert's sense for the structure is doable. And this depends crucially on being able to solve this. This is for me, I really like, I think of this as a very special case of model Lang. In general, if you could replace k to the n union L to n by any finitely generated group over the multiplicative group over the reals, or the complexes, and the solutions in non-degenerate would still be finite, but we do not know how to compute them. So even as far as I know, if you take the group generated by k and l, not the union of these, then it is not known whether the set of solutions in this multiplicative group is computable or not. I think, that's somewhat stunning. The proof that they use is, again, they use to prove it that this set is computable is really just, again, an application of Baker's theorem. All right. I want to say a few words over the reals. Okay, if you can draw addition, then it's actually known that the theory is decidable. A little bit more is kind of this our results spark a little bit of work in this direction. It's not only the first order theory that is decidable in this setting, it's also the second order, the monadic second order theory. So you're allowed to quantify subsets of it. But that is really kind of different. The addition really makes a huge difference. And this is using automata theoretic methods again. I want to say a little bit, this is the last slide, I want to say something about the reals. So I said at the beginning a little bit saying that if you have the multiplication in this structure, then we knew that this is undecidable. But the proof that I gave here, that also works with the reals. It really it depends on how powers of 2 and powers of 3 or k and l interact with each other. It doesn't depend so much on the domain of R. So this works here perfectly fine too. As I said, if you add if you go back to a single one, then this is an old result over the field. So if you go back to the field and get your expressive power, and then over the reals, it is decidable whenever k is computable. I said in the beginning that if you have 2 of them, it's undecidable. A student of mine in Urbana, he showed that the existential theory of the reals with order plus and k to the n and l to the n is decidable. Well, okay, again, you had to be able to solve this linear equations, then it was decidable. But this is now it's a theorem due to the work of Arimov and co-authors. It is, for me, one of the questions I find still really interesting and I have no idea of solving is is the existential theory of the reals as a field with powers of k and powers of L. This remains unknown whether this is decidable or not. The problem is that with multiplication, I mean, the whole problem, I think, is kind of that in this structure we can talk about Diophantine approximations of kind of the log of k of L and and even inhomogeneous approximation problems. And if you're in a linear case, kind of the questions of how quickly you can converge or how quickly that approximation works, that can be decided, at least in the existential theory. If you have multiplication, you suddenly ask questions about, okay, you have these polynomial functions that converge somewhere, and you have to ask a question: is the Diophantine approximation quicker or slower than these polynomial functions or rational functions? And that I simply cannot do and don't know how to do. All right, that's it. Thank you.